Did everybody get a copy of the notes? Anybody else need a copy of the notes? What about today's lab handout? Did I give that to you yet? Everybody got a copy of today's lab handout? All right. Let's see. Looks like I've got some submissions here of the lab. I'll take that now if you'd like to submit it now. Otherwise, it'll be due in lab. Today we're going to be doing the Bernoulli's equation verification. And we haven't got to Bernoulli's equation yet, but going through this activity in the lab today will set things up perfectly for our lecture on Thursday. So it's good timing. Group A is at 2 o'clock and Group B is at 3 o'clock. Remember, the homework assignment you've got coming up is due on Thursday, and it's just 3 problems long. So any announcements, questions? Yeah. What? One of them is how many points you got right. Oh, this is just for this problem. Oh, so okay. Problem 1, problem 2, and then the sum of the 2. Oh, okay. Yeah. The feedback survey is still available, and I set up a smaller link for that. It'll forward into the survey if you haven't entered your comments yet. One of the common issues that's been raised by a couple of people is time available for the quizzes, and I'll try and react to that. I'll give you a little bit more time to take the quizzes. Also, a few people mentioned classroom disturbances and suggested that it would be better if people didn't get up and sit down quite so much during the lectures or do noisy things, phone calls, eating. I also mentioned it's a little bit distracting when students are texting in class, and so I'll encourage you to avoid that. But like I said, I'd love to have your feedback. I'll leave that survey open until Wednesday, and you know, I'll try and improve the course as I'm able to based on your suggestions. Where we left off last time was just talking about radial acceleration. And remember that Euler's equation described how 2 things change in response to acceleration, either the pressure of the fluid or the liquid elevation, or both really, because Euler's equation was characterizing a change in piezometric pressure in response to local acceleration. And here in the rotational flow that we're going to be talking about today, it's the same thing. We're saying that there's a kind of acceleration, and we want to know how does the pressure change because of that acceleration. You remember in the last class period we talked about how to convert between RPM and radians per second. Does anybody remember what that conversion was? How to go from RPM to radians per second? Because it's going to come up. Multiply by 2 pi because there's 2 pi radians per revolution, and then divide by 60 because there's 60 seconds per minute. Good. So here's where we're going to start. Let's consider that there is a tube like it's shown here, and it's rotating. This is sometimes in these types of problems, it's called a U-tube. I know that sounds funny because of the website, but it's called a U-tube because it's shaped like the letter U. And if it wasn't spinning, obviously the liquid elevation would be the same on both sides. But this is spinning, and so the acceleration drives the liquid surface up on the side that is further away from the axis of rotation. This little circular arrow here indicates that it's rotating about this leg, and that this leg is what's swinging around that central axis. And we're given some dimensions here. We're told from the diagram that there's a 25 centimeter deflection, 10 centimeters from the outside leg to the axis of rotation. Now, the equation that will allow us to find out, for example, in a case like this, how quickly it's rotating is the rotational flow equation that's shown here. Now, it looks similar to Bernoulli's equation that we're going to be touching on in lab today, but it's different from Bernoulli's equation. Now, what this says is if you pick 2 points in the system, it can be any 2 points in the liquid. It could be at this surface and over here. Or it could be at this surface and that surface. It could be anywhere in this continuous liquid. Any 2 points can be point 1 and point 2. And in this case, it doesn't matter which is 1 and which is 2. Remember, in Euler's equation, it was pretty important that you selected number 2 was the one that had the more x or the more z in the direction of the up being z and to the right being x. But in this instance, it doesn't matter which is 1 and which is 2. What it says is that you can know the pressure, the elevation, or the radius away from the axis of rotation, r, between these 2 points as a function of how quickly they're rotating, where the rotational rate omega is expressed in terms of radians per second. So we're going to work a couple of examples today that uses this rotational flow equation. But we measure r from the axis of rotation, and the axis of rotation in this diagram is just as shown. It runs through the middle of that left leg. You'd measure z above some vertical datum, and as long as you measure both of the z's according to the same datum, it doesn't matter which datum you choose. You could say, let this water surface be equal to z equals 0, and then for z2 you'd just say 0.25 meters. Or you could measure from the bottom of a U-tube, or you could use the top of the right leg water surface, and then z1 would be a negative value. So it doesn't matter where you choose your datum to be. And it's really important. One of those commonly made mistakes by students is that they first forget to subtract. You know, that's plus here. You add the pressure head and the elevation together, and then you subtract this quantity omega squared radius squared divided by 2g. It's not the Bernoulli's equation. Bernoulli's equation is a little bit different. We'll talk about that in lab today. But just as a kind of a kickoff example, we could use this equation in this instance to find out what's the rotational rate in radians per second for a U-tube that's shown there. And we know that the deflection is 25 centimeters, and so for us, what we could say is let's have the 2 points that we're going to analyze in this instance be, we're going to choose this to be location 1 and this to be location 2. And those were selected for some reasons that are pretty specific. We know a lot about location 1 and location 2 as drawn on the board there. If we'd selected other locations, there'd be too many unknowns. But we already know a lot about location 1 and location 2. For example, we know that the pressure at 1 is equal to 0 gauge. You know, it's equal to the air pressure. Both of these U-tubes are open to the atmosphere. And that's why the water surface could rise the way that it did. If it was an enclosed U-tube where it had been sealed and the water had nowhere to go, then it wouldn't have rised over on that right leg like it did. But in this case, it's open. And since it's open to the atmosphere, right at the interface of the water and the air above the water, the pressure is equal to each other. And so pressure at 1 is 0, and the pressure at 2 is known to be 0. The other thing that we know is we've selected 1 to be right on the axis of rotation, and so R1 is equal to 0. And that's pretty convenient. What we know about R2 is it's 0.1 meters. That's the distance from here over to there. So it's 0.1 meters. Okay? So we will say R2 is 0.1 meters. We can select Z1 to be equal to 0. We'll just say that this is our elevation datum, and then measure the elevation of 2 to be above that by 0.25 meters. And so really the only thing we don't know that's going to be going into this rotational flow equation, the only unknown is omega. How quickly is it spinning? That's causing the situation that we can see on the screen. All right, so just writing the rotational flow equation, P1 divided by gamma plus Z1 minus omega squared R1 squared divided by 2G is equal to the pressure 2 divided by gamma plus Z2 minus omega 2 R2 squared divided by 2G. Okay, because the pressure at 1 is 0, we cancel out that term. The elevation, we're letting Z1 be the datum, so that term cancels out. Point 1 is right on the axis of rotation. So we said let R1 be equal to 0. And so that cancels out this whole term. That's a little bit strange that all three of the terms on the left-hand side are canceled out now, right? Now, what else do we know? That the P2 is equal to 0. And so the only terms that are left are Z2 and this omega squared R2 squared divided by 2G. And if we're trying to solve for the rotational rate, what we'll have is Z2 is equal to omega squared R2 squared divided by 2G. And so we can rearrange that to solve for omega. And its omega is 2G Z2 divided by R2 squared and take the square root of that. Okay? So why don't you substitute in the known values and find out what's the rotational rate? How quickly is that leg spinning in terms of radians per second in order to cause the deflection that's shown?
When you measure the 25 centimeters,
Mm-hmm.
is it, I mean, it's like a millimeter slide. Is, like, I guess if we were doing this experiment, like an experiment,
Yeah.
would we be looking at the top? Because if the pipe was wider,
Yeah. Well,
dead center of
it depends on where you said is 2. And so if, you know, if it was sloped like this, if the water was sloped and then I pick this to be 2, then I would just have the R be to that part. See, so, you know, where along that slope to select depends on what you say the radius is. Yeah. Okay, so it's going to be 2 times 9.81 meters per second squared, Z2 0.25 meters, and the radius 0.10 meters squared. We take the square root of all of that, and we should get that the rotational rate omega is 22.15 radians per second.
what would your conversion from meters per second squared to radians per second?
You're thinking in terms of this earlier slide, what we were looking at here? We don't actually use the radial acceleration in this problem. So in this problem, I have g, the elevation, and then just the radius squared. And so, yeah. The radius that we used of 0.1 meters is the distance from the axis of rotation over to 0.2, so the radial distance from the axis of rotation. Now, we get 22.15 radians per second. If we wanted to convert that into RPM, then we would divide by 2 pi revolutions, radians per revolution, 2 pi radians per revolution, and then we would multiply by 60 seconds per minute, and then that would give us 211.5 RPM. And so 22.15 divided by 2 pi gives us about 3.5 revolutions every second, and then multiply that by 60, and that gives us 211.5 revolutions per minute. So it's spinning around really quickly. Back in the lab, the environmental lab has a centrifuge, and centrifuges are sometimes used in medical applications. For example, if you've ever had your blood drawn, sometimes they'll put your blood in a centrifuge to try and separate like the platelets from the white blood cells, and I don't know, separate the fats out of the liquid and so on. And how quickly the centrifuge is able to separate the blood depends on a couple of factors. It depends on how quickly it's spinning, of course, but it also depends on the axis of rotation, how far away it is from how far away the little test tube is from the central axis of how it's spinning. And in part B of this example, it asks the question, what is the acceleration experienced in the right leg? How many G's of acceleration, for example? And sometimes fighter pilots or astronauts talk about how many G's they've experienced. And by doing that, we say that 1 G would be 9.81 meters per second squared. In the earlier slide, we had the equation that the radial acceleration is omega squared times r. And the rotational rate in this example that we determined was 22.15 radians per second. We square that, and it's 0.10 meters from the axis of rotation out to location 2, and that is 49.05 meters per second squared. And so that's the acceleration experienced out at 2. And it would be more acceleration if it was further away, and it would be more acceleration if it was spinning faster. Since a G is 9.81 meters per second squared, then that is 5.00 G's if we wanted to think of a unit of acceleration being 1 G is 9.81 meters per second squared. So it's 5 G's out at that edge. I think that the maximum acceleration that's typically tolerable for a fighter pilot is around 10 G's, and they can only stand it for a few seconds before they start to black out because the blood can't circulate to their brain. Boy, am I hallucinating, or is there lasers over here? All right. Special forces about to come in here, I think. They're going to attack the computer station over here. There's some way to turn. There we go. All right. Any questions on that example?
Yeah, I still don't understand the units.
All right. So you're wondering why it is radians per second in here? Where does it come from? Well, really, radians isn't a unit, and so you can think of radians as like a unitless unit. So what we should be asking is, how does this quantity come with inverse seconds? And so here's meters times meters, so that's meter squared, and down in the denominator we have meter squared, so the meters cancel out. All we're left with is seconds to the -2 power, and we're taking the square root of that, so it's left with inverse seconds. And so it's just the units that will come out of omega is just inverse seconds. I guess, yeah. Yeah, radians is kind of a special case. Yeah, I don't fully understand that myself, but it's just it's a unitless measure of angle, I suppose. Yeah.
Just put radians per second and do that.
Yep.
Okay.
Yep. That's what needs to go into omega in this formula, and if that happens to be what we're solving for, that's what will come out.
Is this part B, kind of like those wind turbines that we talked about that, being like they're a little slow, so far apart?
Right. Yeah. Yeah, like one of the risks with wind turbines out in the real world is that they can throw ice like hundreds of feet, because up in Minnesota and the upper peninsula of Michigan, where it's really, really cold and also quite windy, they'll have big commercial wind turbines set up, but then sometimes there can be freezing rain that accumulates on the end of those wind turbines, and so they're spinning around, and then they'll throw a big gigantic piece of ice. It may weigh 1,000 pounds of ice that will get let loose, but even though it looks like the wind turbines are moving pretty slowly, because the radius of those blades is so long, and you maybe have seen them driving down the freeway before, like on a truck. They can be 100 yards long easily. At the end of that really long radius, even though it seems to be rotating slowly, the acceleration is really high, and so the reason why it can fling chunks of ice really far and into a house potentially is because the acceleration is really high. And the radial acceleration formula tells us that it's not just that it's moving at rotational rate, but it's also the distance from the axis of rotation that develops that acceleration. So back to these U-tubes. Here's an example I'd like you to take a crack at. We've got an enclosed U-tube. Now this is a little bit different from the open U-tube. Remember, in the open U-tube, what could respond was the water elevation could vary as it was accelerating. Now in this instance, the water elevation is fixed. It's full of water. This U-tube is full of water, and so it starts to spin. And so now the water elevation isn't going to respond to the spinning, but the pressure will. So I've told you a couple of points that we're going to be selecting. We've got location L and location M. And that's what you're going to select as 1 and 2. It doesn't matter which is 1 and which one is 2. We know that the pressure at L is 2.75 kPa, and the axis of rotation distance from the center of the axis of rotation over to L is 38 centimeters, and then from the axis of rotation to location M is 13.3 centimeters, and then the vertical deflection between the two is 12.5 centimeters. And so in this case, I'd like you to try and calculate what is the pressure at M, and there's a couple of tripping hazards on this problem. The first is that the density of the liquid, and therefore the specific gravity, isn't just going to be 9810 newtons per cubic meter. It's given that the specific gravity of the fluid is 0.85. So you're going to need to calculate a different gamma for this than the gamma for water. And then the other tripping hazard is the fact that the rotational rate here is defined in terms of RPM. And so you'll need to convert that into radians per second. So see if you can calculate, substitute everything into the formula that's known, and calculate the pressure at M. All right. In the example, we start off by rearranging the rotational flow equation to solve for P2. Now I've said let's let L equal 1 and M equal 2. And we know the elevation of Z1 will be 0, Z2 will be 0.125 since location M is 12.5 centimeters above location L. R1 will be 0.38 meters because It's 38 centimeters from the axis of rotation out towards location L and 0.133 meters for R2. Converting the rotational rate from RPM, 25 RPM into radians per second, it's 2.618 radians per second. Now, we can substitute in the unit weight of the liquid here, which is 8338.5 newtons per cubic meter because of the specific gravity that's given, and take into account all the other factors here. Ordinarily, the pressure would be quite a bit different, because if it was just because of hydrostatics, remember, all we'd have to keep track of is the delta H times gamma to find the pressure difference between L and M. It would just be a matter of delta H times gamma. But here, location L is further away from the axis of rotation than location M. And so part of the reason why the pressure is higher at L than it is at M is because it's deeper down into the fluid. But then the other part of it is the fact that it's further away from the axis of rotation, and so it's experiencing more centripetal acceleration. And the point that has the more centripetal acceleration is going to be experiencing a greater pressure. Here, the elevation of the liquid can't respond to the acceleration because it's capped. This tube is sealed. And so what responds instead is just the pressure. And if we go through all the calculations, we find the pressure at location 2, which is M. The pressure at M is 1339 newtons per square meter. Any questions about that one? So both of these first examples were relatively easy because either the liquid couldn't respond its position, as was the case here, or in the earlier example, there was a certain deflection, but the deflection didn't go beyond the tube's capacity to handle it. In this next example we're going to take a look at, there's the case that we want to find out what's the equilibrium elevations. And so here the unknown is the Z. It's spinning a certain amount that's defined. Omega is given as 8 radians per second. And obviously the locations we're going to want to pick for 1 and 2 are the locations where we know lots of information, so we can cancel out parts of the equation. You know, we could choose let 1 be down here and let 2 be there. We could substitute that into the equation, but then the problem with that is that it's not really keeping track of the liquid elevations. And so what we want to do, what's shown right now is before it starts rotating. That, you know, the confusing thing is that the picture is showing two things simultaneously. It's showing the before water elevations, and then it's showing as it starts to rotate where the axis of rotation will be and what the rotational speed will be, 8 radians per second. So on which side of those two legs will the water elevation rise, and which side will the water elevation decrease? So we've got the right would rise and the left would decrease, and that's correct. Why is it? Why is it that we'll expect the water elevation to rise on the right and decrease on the left? Why? All right, so there's more length between, he's noticing that it's further from the axis of rotation out to the right leg than it is to the left. So what? That's my response. So what? All right, so you're thinking about it in terms of if you're subtracting what has more. So if R2 is bigger, then that means that Z1 is going to have to be smaller, right? Okay, good. That's definitely one of the ways to analyze it. Another way to analyze it is to think back to centripetal acceleration and what's the formula for that. And so in centripetal acceleration it says that the acceleration is omega squared times r. And the reason why I bring that up is which one of the sides has more acceleration? The left side of the leg or the right side? Which of those two has more centripetal acceleration? It's going to be this. Even though they're rotating at the same rotational rate, they're both rotating at 8 radians per second, the right leg has more distance away from the axis of rotation, and so this has more acceleration. And remember, the pressure increases in the opposite direction of acceleration, or the elevation increases in the opposite direction than acceleration. And so if this has more acceleration, then the pressure or the elevation is going to respond in an opposite way to that. And so we want to find out where is the water going to be when it's rotating at 8 radians per second. So here z is going to be the unknown in this equation. Yeah.
Can you think of the axis of rotation is the way it's rotating, so the section to the right there, is that positive? And would that radius be positive and to the left be negative radius? Because the negative cancels out squared.
Well, the first thing I need to point out is it doesn't matter if it's going clockwise or counterclockwise. And so there's no significance to whether it's clockwise or counterclockwise, and there's no significance to what we consider 1 and what we consider to be 2. And so having said that, can you rephrase what your question is?
Well, I mean, so even if it was rotating clockwise, then the section to the left would be positive. I guess the way it's rotating, does that affect which radius would theoretically be positive or negative?
They're both positive values as drawn here because you know, there's the negative built into the equation here, but they're both some positive distance away from the axis of rotation right now. So it doesn't, you know, neither of them are going to be, you wouldn't substitute a negative number into R1 or R2. They're both positive numbers. All right, so this one's a little bit more complicated because we're going to choose a z value. You know, we're going to choose some location to be our datum, but the datum is going to be getting lower as it starts to spin. You know, there's the before and the after. What I've drawn here is the after. We could say before it started spinning, the water level was like this. So before it started spinning, there was 0.18 meters on both sides. 0.18 meters on both sides. And then it started to spin, and we don't know what the equilibrium elevations are going to be once it's spinning. Well, let's just start with what we do know, and then we'll start thinking about what we don't. The first thing is that we do know the R1 is 0.18 meters. And what I do is I'll just pick location 1 to be whichever is closer to the axis of rotation, but like I've said before a couple of times, it doesn't really matter what you select as 1 and what you select as 2. R2 is 0.36 meters. Omega is 8 radians per second. Let's use the vertical datum to be the bottom of this tube. And so if we have the bottom of the tube be our z datum, what we can say is that z1 plus z2 is equal to 0.36 meters. Now that's always going to be true, before it's spinning and after it's spinning. Why will that be true after it's spinning? And the before is obvious because if you add 0.18 and 0.18, that's equal to 0.36. But Michelle, how will that continue to be true once it does start to spin? Okay? So for every centimeter it goes down on the left, it will increase by a centimeter on the right. So it's going to, the same water is going to be in there. The same amount of water is in there. It's just it's changing location. It'll go down a little bit over here. It'll go up a little bit over there. And so what we can say is that both of them together is 0.36. Or in other words, we could say Z1 is 0.36 minus Z2. All right. Now, let's say that we pick location 1 to be whatever our water elevation is on the left. So this is Z1, and here is Z2 after it's spinning. And we can say that the pressure at 1 is 0, so we can cancel that term out. Z1 minus omega squared R1 squared divided by 2G. There's P2 divided by gamma plus Z2 minus omega squared R2 squared divided by 2G. And this term is also going to cancel out because it's atmospheric pressure at both of the location 1 and location 2. The difference in elevation, Z1 minus Z2, is going to be omega squared divided by 2G, and then it'll be R1 squared minus R2 squared. And so I've moved this term over to the right-hand side of the equation and then extracted out the common factor omega squared divided by 2G, so that what's left is R1, and it's positive since it was negative and it moved over to the other side of the equation. Now it's positive R1 squared minus R2 squared. And we can substitute, since we know Z1 is 0.36 minus Z2, I'll make that substitution over here. I can say, instead of Z1, it's going to be 0.36 minus Z2. All right, so if I then rearrange all of that just to be in terms of Z2, it is omega squared divided by 2G R1 squared minus R2 squared minus 0.36, because I moved the 0.36 to the right-hand side of the equation, and then all of that is divided by negative 2, because I had two Z2s and it was negative. So if I divide by negative 2, divide both sides by negative 2, then that's how I isolate Z2. And so with that expression written, I can just substitute in all the known values and find out the elevation of location 2 above the datum. And so it's 8 radians per second squared divided by 2G. And 0.18 meters squared minus 0.36 meters squared minus 0.36 meters, and all of that is divided by negative 2. Okay. That gives 0.3385 meters. And that is Z2. And so then if we go back over to here and find out what is Z1, Z1 will be 0.36 minus 0.3385 meters. And that is 0.0215 meters. So that's how you can apply this procedure to find out where are the equilibrium water elevations going to be when it's spinning a certain rotational rate. I'm really glad you asked that. That's a very, very good question. And to answer your question, I'm going to ask another question. What if instead of spinning 8 radians per second, what if it's spinning 14 radians per second? So his question was, can the water level go below 18 centimeters? So, like, the water level over here is only 0.0215 meters. So that's essentially 2.2 centimeters when it's spinning 8 radians per second. My question is, what if we spin it faster? Then what happens? So when it was not spinning at all, it was 18 and 18. And then we started spinning it. This level was going down. That level was going up. So what if we spin it a little bit faster? Then what's going to happen? It's going to go down further, right? And so what if we spin even faster than that? Then what's going to happen? It's going to continue climbing in the right leg. Try and solve that. Use the equation we've set up already. This is going to be the equation I'd like you to substitute into. But substitute in an omega of 14 radians per second instead of 8 radians per second. And let's see what happens when it's spinning really fast. What? Yeah, what if the rotational speed turns up to 14 radians per second? So what would be the elevation if it's spinning that quickly? What was that? 66.55. Yeah. And so if the water level is that high, then what do you get for Z1? Right, negative number. And so the water level can't go below the tube elevation. And so what that tells us is there's a certain point at which you're spinning it so fast that the water exits the left leg, and actually now the water is starting to move over here. So the interface is in the leg itself rather than in one of the sides. It's in the base, and the water level is continuing to rise on the right. And so, you know, what's happening? Where are things when that's occurring? We need to come up with a different expression for that. The water starts to travel in the base of the tube. So if for omega is 14 radians per second, what you should have gotten was a Z2 of 60.6655 meters, which would then yield a Z1 of negative 0.3055 meters, which means it's below the base. And that doesn't work. Can't do that. So that's our hint that the water level is the interface is in the base tube now. So it's more like the water is more like this. So here's the axis of rotation, and the water level's here somewhere. Okay. So how do we solve that? The area of the tube?
Well,
The volume? All right. You're definitely headed in the right track. We need to find out the total amount of water that's inside of there. And we don't necessarily have to find it in terms of volume, which is lucky because we couldn't. We don't know the diameter of that tube. Those tubes could be a centimeter in diameter. They could be larger or smaller. I guess maybe we could try and scale it somehow based on the dimensions that are given, but it looks like those dimensions may not be, this drawing may not be to length because it looks like maybe, I don't know, those aren't the same 0.18 meters. What we can say, here's what we know. How much water? What's the total water amount inside of the tube? So the total amount of water that's in there is we've got 0.18 meters in the left, and then we've got that 0.18 meters from the axis of rotation out to the left leg, and we've got a 0.36 meters from the axis of rotation to the right leg, and then we've got the other 0.18 meters from inside of the right leg before it starts spinning. And so the total length of water inside of that tube, there is 0.90 meters. Now when it spins, it's just going to be changing the location of it. The amount won't change. It's just where it begins and where it ends is going to be moving from side to side depending on how quickly it's spinning. And if the water is down inside of the base leg, then what we can find is an expression that tells us Z2 in terms of R1. And so there's a relationship between Z2 and R1. And what we can say is Z2 is 0.54 meters minus R1. And the way that we come up with that is if all of that, if the water was just right here, you know, like the water level is there, then it would be no, I think actually I'm thinking in terms of 0.54 is 0.18 times 3, right? Okay, so if the water level is here in the center, then it would be 0.54 on the right. And so in other words, you can have R1 be in terms of the Z2, like if the elevation in Z2 is, if R1 is equal to 0, then Z2 is 0.54. If R1 is more than that, then the water level would come down a little bit. So if R1 is 5 centimeters, well, I'll do it in terms of meters. If R1 is 0.05 meters, then Z2 would be 0.49 meters. Or it might be that actually the liquid level is over to the right. So it might be that the water is here. And in that case, we'd use a negative value. That's now finally when we'd start to use a negative value for R1 is if both of them are to the right of the axis of rotation. And so if R1 was negative 0.05 meters, then Z2 is going to be 0.59 meters. Does everybody see how this one works? Because we need basically some expression that tells us how high is the water in the right leg as a function of where is the water in the base. In the previous part, before it was spinning so quickly, we had an expression that related the water in the left leg and the water in the right leg. now that the water is down in the base, we need an expression that relates where is the water in the base compared to the elevation of the water in the right leg. And that's what this expression is going to be able to do for us. This general expression is going to be valid for any particular R1. So R is going to be variable and Z2 is going to be variable. R2 will remain constant because here is going to continue to be location 2. Location 1, though, is going back and forth depending on how quickly it's spinning. 0.54? It's just because of how much water is there. Like, I'm assuming that if R1 is 0, and so if the water is right at the axis of rotation, then how much water is in the right tube? Now, I added up all of these, so there's 0.9 total length of water. And so the Z2 would be 0.54 if R1 is 0. That's how that equation came together. And now, at this point, remember what we have is a negative value for R1 if the liquid surface is to the right of the axis of rotation. Okay, so let's see if this will allow us to find out what's going on when it's 14 radians per second, because that negative value we got before didn't make any sense. Now, substituting into the equation, the general form of the equation here, we're going to continue to have the pressure is equal to 0 still at 1 and at 2, because location 1 is the interface of air and water. Here is going to be location 1, and it's air, open to the air, so that's why we can cancel out P1. And Z1, since location 1 is in the base leg, then that allows us to cancel out Z1 as well. R1, we can't cancel that out. P2, though, location 2 is in contact with the air, and so it has pressure of equal to 0. Z2 is unknown, and we're going to substitute in some value for R2. And the equation that we've got, therefore, is negative omega squared R1 squared divided by 2g is equal to Z2 minus omega squared R2 squared divided by 2g. And so that can be switched around to look like omega squared R1 squared divided by 2g plus 0.54 minus R1. So I've made the substitution for Z2. I moved this over to the right-hand side, and I'm going to have all of this equal to 0 here in a minute when I've finished. So this was the substitution for Z2, and then it is minus omega squared R2 squared divided by 2g. It's equal to 0. Okay. So again, just moved this term to the right-hand side and substituted in the expression for Z2, which is 0.54 meters minus R1. Now I'm going to substitute in the known values for omega is 14 radians per second. Okay, so that substitution is going to be 14 radians per second squared, R1 squared divided by 2G minus R1 minus 14 radians per second squared and 0.36 meters, because we know what R2 is, divided by 2G, and then plus 0.54. That is, that number. I've just moved it over to the right because what I'm building is an equation we're going to have to find roots for, is equal to 0. Okay, so if we do the calculations for that, it's 9.989 R1 squared minus R1 minus 0.7547 is equal to 0. Okay, so the roots can be found for that expression. Why don't you do that with your calculators? I know you've got the ability to find roots of equations, and see if you can select which of the two roots is valid for R1. Okay, the two roots here are negative 0.2293 and positive 0.3294. So the question is, which one of those two is the right root to select? And that's a little bit tricky, because ordinarily we think, oh, a negative number, that must be some sort of a solution that doesn't make sense. But in this case, a negative number might make sense, and the positive number might not make sense. If it's positive, what that's saying is, if for a positive R2, that would mean this is, for a positive R1. This is R in the positive direction. And so could 0.3294 work? Well, no, it couldn't work because we only have 0.18 centimeters that R1 can be to the left of the axis of rotation. On the other hand, this negative root of 0.2293, that would indicate that the water level is 22 centimeters to the right of the axis of rotation. That's what the negative number means. And so actually that's the correct root. So when it's spinning at 14 radians per second, then the water level is such that it is 22.9 centimeters this way from the axis of rotation of the water surface at 1. And then we can find the Z2 from that. The Z2 will be 0.54 meters plus 0.2293 meters, and so 0.7693 meters. And that's the elevation. That's how far it is up on the side here Z2 is 0.7693 meters. Well, it just didn't make physical sense for the positive value to be correct. If the positive value is correct, then what that would mean is that the water elevation is what's the positive root? 0.32. And so we can't go 0.32 meters from here to the water because the tube itself is only 18 centimeters long. So there's two things going on here. I guess we had some complicated algebra a little bit. You know, the physical situation of the tube got a little complex, but the main concept you need to know for this part of the course, you know, what's the fluid mechanics here? The fluid mechanics is acceleration causes a change in pressure. We already knew that from Euler's equation. In Euler's equation, it was local acceleration that was causing a change in pressure. You know, it's that tank of water that's getting accelerated to the right and accelerated down from the homework problems, and you found what's the change in pressure because of that. Here, there's a change in pressure because of rotation, either a change in pressure or a change in elevation. And this equation can be used to find at any location inside of the system, you can find the pressure at that location or the elevation of it as it responds to the centripetal acceleration that occurs when you've got it rotating at some rotational speed omega. So that is it until I see you for lab today. We're going to be doing Bernoulli's equation in the lab. I'll have Group A at 2 o'clock, Group B at 3. Question?
So we can't use this Z2 equation for when it's going to be lower than the left side because that came up with two different answers, which is why what I don't understand.
So we can only use that when the water level is continuing to be in the base leg on the left. Yeah.
So if, say you did do that.
Once the water level's in the horizontal, then we can't use that anymore because remember it was assuming that Z1 and Z2 is always going to be 0.36 together.
Okay.
Yeah. All right, I'll see you in lab.
So is there going to be a test question?